And welcome, friends, once again for today's lecture, which is on scientific payload development for solar system exploration. So, we listen to many discoveries which are happening from several scientific missions. So, the question that comes is what all go into it to make a scientific discovery? And it is quite obvious that the scientific instruments will have a significant role to play behind any scientific discovery which you're making from space. Now, at this juncture, it is appropriate to do a small recapitulation of my previous lecture, where I have spoken about the overview of space science and exploration. So, during my previous lecture, I have discussed about the importance of the space-based observation over the ground-based observation. So, I have made a mention of the advantages when you are sitting beyond the atmosphere and you are not letting the atmospheric effects to come in the way of your observation, and sometimes you are even sitting outside the magnetosphere itself. So what advantages you get, all these things we have discussed in the previous lecture. And in the previous lecture we also made a mention, when we say we are observing or going to observe some quantity, what all we observe. We have discussed, we observe some celestial bodies, we observe some some processes, and in the celestial bodies also we have gone to the more details. We mentioned that we observe the interiors, we observe what is happening in the subsurface level or the surface level, or what is happening in the atmosphere. All these things we have discussed, and while we discuss those, we also have touched upon one topic, that sitting from a distance, when we are making a measurement, that is when we are making a remote sensing kind of measurement, what are the messengers that carry the information to us? Us means the instrument which is sitting. So we have also seen that electromagnetic radiation or photons, they are playing a significant role as messengers, but they are not the only messenger. There are other messengers also, like charged particles. There are also messengers like gravitational waves. So we discuss those aspects also. Now here, as a prelude to the present discussion, I want to make a mention. See, we observe the world with our five sense organs, right? But the five sense organs have got their own limitations. If you speak about the eyes, it cannot see beyond a certain wavelength range. So, but a lot of phenomena which are happening, they are manifesting themselves at the other wavelength region, in the infrared or even longer wavelength regions, or even in the ultraviolet and the shorter wavelength regions. So, how to do? So, man started augmenting the capability of the sense organs with instruments, and those instruments started flying to space. And when we say the instruments which are flying to space, that gave some extra edge to our perception about the universe. And at this very juncture, you have to be very, very careful, because I am telling about instruments which are flying to space. And let me tell you, there are two kinds of instruments which are sent to space. When I say there are two kinds of instruments which are sent to space, one kind of instrument is the instruments which are needed for any space flight. If you are sending a rocket, or if you are sending a satellite, there are certain electronic systems which are needed to ensure that a rocket gives you the proper access to space, or a satellite is doing its job properly, whatever it is supposed to do. So there are many such systems we will see. But apart from these regularized instruments, which are anyways the part of any rocket or satellite, there are different kinds of instruments which are called the scientific instruments or scientific payloads. So in our discussion, we will use the two terms scientific payloads and scientific instruments interchangeably. Okay, so let's have a look about the kinds of instruments that we generally fly to space. Number one, the category is avionics. So avionics is a term which is used for aviation purpose electronics. The electronics which is for the purpose of aviation, it could be a part of an aeroplane, it could be a part of rocket, it could be a part of a satellite. So what are there? You have systems for telemetry, tracking, telecommand, all these things we discussed in the previous lecture. Then we have systems for navigation, guidance, control, power systems, and others. But you have to remember, all these things are mission critical. Mission critical means if the power system fails, the mission is failure. Or if the navigation guidance control doesn't work, the mission is no more. And here, because of this reason, every mission also applies this, and there are certain specialties with respect to avionics, like they are highly standardized. Their inputs and outputs are well known. Suppose we know in the navigation guidance control system, the inputs should come from the gyros or the accelerometers. So how much is the voltage level which should come at the input, and what the instrument should do, what should be the output of the instrument, all these things are known. And they're very much testable. And in many of the cases, redundancy is available. Redundancy, as you may remember, you have a similar device, one extra. There may be a possibility that both the instruments can work together, like our kidneys work, right? They work in hot redundancy. So if one fails, the other continues to work, or cold redundancy. Okay, so if one fails, the other understands that the second one needs to be switched on, and then it takes over. So these are the features which characterize the avionic systems. Now, if you come to the scientific instruments, they're different. And the first question comes, how do we define the scientific payloads? So we can define it like this. Scientific instruments or scientific payloads are the instruments for space-based scientific observation of celestial bodies, fields, and processes. Now, I have mentioned that there are significant differences between the scientific payloads and avionic systems. So what are those? One is scientific payloads may subject it to a situation where the signal they have to measure is very feeble, unlike the avionic systems. Or it may so happen that it is supposed to measure a wide range of inputs. At that point, you will start thinking whether one instrument is sufficient, or whether I will break the requirements into 2-3 instruments. Such a big range, if you have to cater, one payload may not be sufficient. So that is another kind of thought process which goes into in the building of scientific instruments. And the scientific instruments may be very sensitive. It may be sensitive to contamination, like dust contamination, contamination with respect to grease, or some other, gas molecules. It may be subjected to the spacecraft charging, which is also detrimental to some of the instruments, which basically measure the fields. And it also may be sensitive to the magnetic fields, especially for the magnetometer kind of instruments, which are destined to measure the magnetic field of, say, celestial origin. And you're mounting as a part of the spacecraft. The spacecraft has its own magnetic field, which may interfere with the magnetic field which you're going to measure. So there are certain sensitivities which are typical problems of a scientific payload. Avionic systems are not having to do anything with this. How much testable? You can test an avionic systems completely, but the case may not be same for scientific instruments. It may not be fully testable. And one important point you have to note, there is no redundancy in general for any scientific instruments, because they are not considered as mission critical. So I hope I could explain to you the basic differences between these two categories of instruments. If the first category of instruments are comparable with military, they are all well-defined, well-disciplined, standardized. Second category of instruments, scientific payloads, they are more like poets or very creative people. They are very sensitive. They are different. You cannot match one with the other. So now, in the previous lecture, I also have mentioned about two kinds of observations which we do from space. One kind of observation is in situ observation. Another kind of observation is remote sensing observation. So when I say in situ observation, I mean the instrument is directly interacting with the subject of measurement. From biology, you may come up with a very easy example, our nose. So if I have to smell a mango, I will take the mango, in such a way that the molecules which are coming out of the mango would directly interact with my nose, and then I would be able to get the smell of the mango. But the remote sensing measurements are such that the instrument remotely senses the subject with a few messengers coming from the subject. Here you take the same example of a mango. I want to study the mango. I keep the mango at some distance, and with my eyes I look at the mango, and the light which is coming out of the mango, they're carrying the information about the color of the mango, shape of the mango, texture, so on and so forth. Now here is a catch between these two, in situ and remote sensing observations. In remote sensing observations, we often need the knowledge about the medium of propagation of the messenger. In this case, light which is coming through the air or vacuum. Properties of this medium has to be known, because ultimately the measurement which we are going to do with my instrument is actually having a mixture of information from the subject which is under measurement, the properties of the medium which is carrying the information, and of course the property of the instrument itself. So all these three things are mixed in the ultimate measurement. So it is a bit different ball game from the in situ observations. And I need not mention that when I am making a remote sensing measurement, I can have many types of messengers. I can have particles as messengers. I can have radiation as messenger, fields as messenger, so on and so forth. In this slide, I have not listed everything. Now, there are certain fundamental challenges for scientific instruments. One challenge is the type of signal which has to be handled. You don't have any control like you have for the avionics systems. As for a scientific instrument, it is exposed to the whimsical behavior of nature. The way nature presents itself, the scientific instrument should be able to capture its feature like it is. Okay, so watch as it happens. It is true for a scientific instrument. So when it comes to scientific instruments, it is nature that decides the input. And the natures could be like this. It could be a continuous signal, like continuously sun is emitting solar wind, and or some radiation is coming from a celestial body to measure that. Or it could not be continuous, it could be sporadic. Sometimes it is happening. In bursts, it is happening. So some example is the coronal mass ejection from sun, or some scintillation which is happening in the, say, of the electromagnetic waves when there is a refractive index variation in the troposphere, or in the ionosphere when the scintillation is happening. Gamma ray bursts, all these are sporadic events. There could be another categorization of the kinds of signal. It could be feeble, it could be strong, it could be active measurement, it could be passive measurement. Coming to the example of active measurement, say radar-based probing. If you're having a radar on a satellite, you can send electromagnetic radiation and analyze the electromagnetic radiation which is reflected or scattered back from the subject. So that is an example of active measurement with a scientific instrument. One example is synthetic aperture radar. There could be another type of measurement like passive measurement, wherein you are not sending anything, but whatever is coming out of the instrument, you are making a measurement. Typical easy example is your camera. If you're having a camera on board, a satellite, it is measuring with respect to the light which is coming out of the surface. Okay, there are many such examples. Now, these not only the signals are different kinds, there are different kinds of requirements are there for different kinds of scientific payloads. One example is some scientific instruments may demand the utmost cleanliness against outgassing. Suppose examples of the mass spectrometers. Mass spectrometers are like electronic noses. Okay, so if you touch it with your hand, okay, by when the mass spectrometer gives you a spectra, it will show you the spectra which is coming from the dust or the sweat which has come from your hand onto the instrument. Not desirable. There could be another requirement like you have sent particle detector or field detector in a satellite, and there is a spacecraft charging due to any reason that you cannot stop. But what you can do is you can do a proper grounding of the instrument. And if there is an information available on the spacecraft charging, that you can use to correct your data. There could be some instruments which require magnetic cleanliness like magnetometers. Some instruments are very, demanding about the requirement of low temperature, especially the infrared measurement systems where the infrared detectors are cooled so that it is not disturbed by the thermal noise. And some instruments want to have special orientation, like cameras to face the target, or mass spectrometers. Sometimes they want to be along the velocity vector of the satellite. There are many. I have not listed everything. So what I wanted to say is there are 5 or 6 kinds of requirements. And just imagine you have these kinds of instruments in one mission, and each instrument demands something or the other. And it takes a lot of wit, lot of ingenuity to tackle this kind of a problem. So a very quick example of some techniques of remote sensing and in situ observations. Let us start with remote sensing observations. So one technique could be you are using photons as a messenger. Suppose the reflected or scattered light which is coming from the surface of a celestial body, this can be measured. Okay, and what is the prime source of light? Say sun. Sun is illuminating the surface of the moon, and you're having an instrument which is studying the surface of the moon, and the light which is coming out of the surface of the moon, the reflected light or scattered light, whatever it is, your instrument is studying. So what it is studying? Suppose it is studying the intensity distribution. It is basically taking a picture, right? So it is an imaging instrument, camera. Or if you are having a method of filtering the different frequencies or wavelengths which are coming from the reflected light, we call a dispersing mechanism. It could be a simple dispersing system. You can, if I ask you, you will be able to come up with some examples. A kind of device which can disperse a mixture of wavelengths, prism, for example. Or those who have studied a bit more physics can be, you can come up with an example of a grating. Grating is also another example where you can disperse different frequencies. If you such an arrangement, then you can go one step further. Instead of being satisfied only with the imaging, you can do something called spectroscopy. You see the radiation which is coming, it is reaching what wavelength, or whether some wavelength is absorbed due to any reason. That information gives you some tool to understand the process which is happening, or a tool to understand what is the composition of the surface, or the medium which is coming, the medium which is intervening, the subject and your instrument. All the information are coming in the wavelength. And there could be another technique. Suppose again, sun is illuminating on the surface. Let us take the example of the moon. And the solar high energy photons, say X-ray photons, they are exciting some of the atoms on the surface of the moon. So what happens when an atom gets excited? The electron has a transition from the lower energy state to the higher energy state, right? So, but that state is not long-lived. It is a short-lived. So the atom undergoes a relaxation. So electron comes down to a lower energy state from the higher energy state. And what happens in the process? This process is known as a process of relaxation. In relaxation, a photon comes out, and this photon is often in the X-ray region. Okay, so the X-ray photon which comes out of the process of relaxation is captured by your instrument. And this is a technique which is known as X-ray fluorescence, XRF. So which gives you a lot of information about what are the elements present on the surface of a celestial body. It could be a part of mineral or not, whatever. It gives you elemental level information. Okay, so that is one kind of remote sensing instrument. Another kind of remote sensing instrument could be active remote sensing, as I mentioned. So you send a signal, you receive it back, part of it, and then you get the information about the planetary surface, or in the not only the roughness of the surface, it could also tell you about the kind of minerals which are present, whether there is a signature of water, either in the form of ice or subsurface. That information you can get. We have reserved a very fancy name for that. When we say water is there on a celestial body, it's a moon, we say hydration is there. So hydration is not necessarily water. Even if you see signatures of hydroxyl molecule or hydroxyl radical, that is also a sign of hydration. It's a very general term. So you have polarimetric studies. So you send a particular sort of polarized light, and the light interacts with the surface and the light which comes back to you may undergo certain change in the state of polarization. So it tells you about surface roughness, surface electrical properties, or surface hydration. This is all about the remote sensing observations. Now, let me tell you about the in-situ observations. In the in-situ observations, you have several techniques. Mass spectrometry, I have mentioned, wherein I compared it already with the nose, human nose. Then seismology. Seismology is another in-situ observation. Suppose you have a small device like this, it is kind of seismometer. You keep it on the surface. What is seismometer? It is basically something which measures seismicity. Seismicity, you know, earthquake. It is seismicity of Earth, or moonquake, seismicity of the moon. Basically, it measures any kind of vibration. It has in it sensors which can measure acceleration. So you have to keep it attached with the surface whose vibration you want to measure. So it is an in-situ measurement. Charge particle detectors, Langmuir probe, every instrument which I have listed is worth describing, but I will not pave that way. Today's lecture is not meant for that. I only wanted to tell you there are several techniques and people are coming up with new innovative techniques for in-situ measurements and for remote sensing measurements. And these are two broad categories of any scientific instrument. Now here, let us come to the discussion what are all present in a scientific instrument. So as I told, there are many kinds of scientific instruments. And if I have to start explaining each of the kind of scientific instrument, this 1 hour lecture is not enough. So what I will do? What I will do is I will present to you a very general picture, a very generic picture of a scientific instrument, which you can fit with any kind of observation. Okay. So I have drawn a block, red color block, which I am calling a scientific payload. And let us see what are the things which are inside it. A sensor, which is along with a filter, which senses the stimulus. A stimulus could be an electromagnetic radiation, neutral particles, charged particles, whatever. It's a messenger which is coming. And the sensor senses. The sensor has to be sensitive to that kind of stimulus which you are relying on. Often it has a filter with it because you may not be interested in the entire spectrum of that stimulus. Okay, for that there is a filter. So at the output, you get a filtered output and there's a detector. There are people who tell sensor and detector interchangeably. So here I will deliberately tell them as different entities. It will be easy to understand. So detectors are the ones which take the filtered output as the input and they give an electrical response, analog electrical response in general, which goes to the electronics of the system. Often we call it the back-end electronics. So what is in the front end? The sensor. And the electronics gives you the digitized or encoded data. At the end of the day, what you have to do, you have to send from the satellite. The analog signal you cannot send. So you have to digitize the signal with the format. And the digitized signal you have to send to the satellite baseband system. The baseband system, those who are aware about the communication technology terms, the signals which are about to be transmitted, which are processed and which are ready in a particular format to be sent through an antenna, they're called baseband signals. Okay, so baseband system, satellite baseband system takes this digitized data or encoded data from the electronics of the instrument, scientific instrument, as their input, and then the transmitter antenna of the spacecraft takes over and they transmit. In between, what happens? There is a power system which powers the scientific instrument. See, scientific instrument needs electrical power, right? So it has to be fed with some power system. So that is one interface which goes. And there is a telemetry system which reads out some parameters from the scientific instrument. That's why I have shown an arrow which is coming out of the instrument. They're called HK parameter. HK means what? Housekeeping parameters. There are some parameters which tell that your instrument is healthy. Otherwise, you will get everything from you're going to get the data from the instrument, but you are not confident whether your instrument was healthy when it acquired the data. So HK parameters give you confidence about the health of the instrument, which in turn boosts the confidence to use the scientific data which came out of the healthy instrument. So and this satellite baseband system is common to many other systems. So if I have to tell you a summary of this slide, what are the subsystems of a scientific instrument in general? Number one, sensor. Number two, detector. Number three, electronics. Number four, it's mechanical housing. Yeah, I call that also a subsystem. To a mechanical engineer, it is very much a subsystem. And the interfaces, which I have just discussed, power, telemetry, baseband system, we call it a data output system, or BDH, bus, baseband data handling, BDH system. There's a fancy name for that. So let us come to the part two. After having introduced to you what all are there in a scientific instrument in general. Now, how to make it? That is the objective of today's lecture. There's a big table, big slides. Don't get baffled with the view of this slide. I will tell you what it is. It is basically a description of something called technology readiness level, TRL. Technology readiness level starts from the basic principle observed and it ends at the actual system which you have flown to space in the space missions. In between, there are steps. Technology concept or application formulated, active research leading. There are many steps which are representing the different stages of development or readiness of your instrument. On the right hand side, I've given some examples. So if you happen to take a screenshot of this particular slide and later on you can revisit, you will be able to understand what is the technology readiness level. In this lecture, I am going to describe you the steps which are associated with making of a scientific instrument. And many a times I will just mention what at the TRL levels do those steps belong to. Okay, but you don't have to remember all these steps right now. This is for the purpose of mapping I have given, which I will refer only. Important thing is to understand the steps which are associated with making of a scientific instrument. So development of scientific instrument, step one. So this step one, what I am telling, it is not TRL one, okay? Step one, whatever I have described here, they're absorbed in TRL one and two. So the step one is you are defining the payload. The functional specifications of the instrument you are defining. Functional specification, what do they mean? Functional specification means, I will tell you what do they mean. Let us see. Those who remember my previous lecture, I have given you a glimpse of how mega projects are formulated, how a mission is formulated, right? So basically you start from a fundamental question and you split this fundamental question to a set of specific questions, set your target, and then identify the domains need to be studied, whether you want to study the surface or interior or atmosphere. Then you identify the parameters which you want to study and specify the ranges of the parameters and identify the techniques which you want to use to study, whether you want to use infrared spectrometry to study or whether you want to use a gamma ray spectrometer to study. That is your technique, and that's how the scientific payload concept comes into picture. And functional definition, functional specifications mean those parameters which you have identified. Okay, these parameters you have to tell from what range to what range you want to study. What should be the resolution of each parameter when you are telling? Suppose I want to make a measurement from say 400 nanometer to 700 nanometer. In this range, that is my specification, functional specification. I can say I will be able to resolve in this range of wavelengths 10 nanometer. So 10 nanometer is my resolution of the wavelength. Again, that is my specification. There could be specification about sensitivity. Okay, so I should be able to have this much sensitivity of the instrument. If this many photon comes, this per voltage and current will be my output sensitivity. So this list, which is shown in the right hand side and top part of the slide, you come to a table which is basically a list of the parameters. Parameter 1, 2, n. I have shown some arbitrary numbers as reference. 5.0 plus minus 0.5. 10.0 plus minus 0.2. These are all ranges of the desired specifications. So after having this done, next what you are doing, you are having to know the intricacies because you are not done with the process. Specifications you have to come across, right? Now, in the previous slide, I have not told you have arrived at the specifications. Now I am telling how you will arrive at the specifications. And this is the most difficult part of the journey. There are certain considerations which you have to consider. One consideration is resolution versus throughput. So I am using a term throughput now. You remember the block diagram which I have shown of a scientific instrument. I have shown on the left hand side some stimulus is coming. It could be electromagnetic radiation, let us say, for simplicity, and there's a filter. Basically a sensor come filter, and you're having a filtered stimulus output, which is an input to your detector. Okay. Throughput means if you send 100 units of the stimulus at the input, how many of them constitute the output, right? So if the throughput is high, your instrument is very efficient, but it comes at a cost. If the throughput is high, means you are not filtering properly, right? If I take an exam and 100 examinees are there who are appearing for the exam, and question paper is so simple, 99 of them pass. What is happening basically? My throughput is very good, right? 99 out of 100 pass the exam. But compromise I am making in the quality of the merit. On the other hand, if I do like this, I want to filter out only the very meritorious students. Question paper is very tough. 100 examinees appear in the exam, only 10 of you pass. So what am I doing? Basically, the throughput is less, but the resolution, that is the merit resolution, is very sharp. So basically, high resolution is less throughput and vice versa. And there is one trade-off you have to decide what you really want, whether you really want throughput or whether you really want very good filtering. And it is very important when you are looking at a very feeble object or very feeble signal. Sometimes you have to consider the need of the throughput rather than resolution. So, or you have to go for very good sensitivity. The problem of very good sensitivity of a detector is another one. The noise of the detector increases. Those who are familiar with photography, if that there is a parameter called ISO setting in photography in your detector. So if your ISO setting is high, you are capable of taking photographs in dark condition also. Basically, your detector is very sensitive. But it comes at a cost of noise. You see grains of noise on the image. It's like that. So I hope these two graphs are self-explanatory. In the left-hand side, I am showing here a very poor resolution but high throughput. Same scale I am plotting, very low, very high resolution. High resolution means the width has to be very narrow. And resolution also, throughput also has come down. So you have to make a trade-off. Another kind of trade-off you have to make is range versus resolution. Let me give you an example. Range means, suppose, let us take an example of a spectral range. Okay. Suppose I want to have good camera, visible camera. So starting from 400 nanometer to 700 nanometer spectral range I will measure. And I will have a resolution of 10 nanometer spectral resolution. Camera means I mean to say spectroscopic camera, spectroscopic imager, right? I am not satisfied only to see the image. I want to do spectroscopy also. And that's why the spectral resolution comes to the picture. So, so far so good. Now, if we say I'm not happy with this kind of range, I want to go higher energy range, that is lower wavelength range. I want to go below 400 nanometers. Suppose I want to go to 200 nanometers. And in the higher side, I am not satisfied with 700 nanometer. I want to go to 1000 nanometers, suppose. Whether I can get the same 10 nanometer resolution? In general, no. So if you go on having a very big range spectrally, suppose, or mass range or energy range, whatever it is, you are going to sacrifice, or it comes at a cost of the resolution. Again, you have to say, really you wish to go for a very big range, and if you are really needing a very big range and a very sharp resolution simultaneously, then you may have to decide whether I need to have multiple instruments covering different ranges. And every wavelength region has a story to tell you, right? So you may need to have different range of measurements and different ranges of measurement. We call it a hyperspectral measurement. Resolution starts crying, what should happen to me? So once you go for multiple instruments, more spacecraft resources are necessary: mass, power, bandwidth. Okay, that also you have to consider. Yet another two parameters which fight among themselves are dynamic range versus sensitivity. Dynamic range is what? Dynamic range is you are measuring a stimulus, a signal, right? How low, how feeble you can measure, and how high or how strong you can measure. So if you make a ratio, that is maximum of the signal and maximum handleable signal and minimum measurable signal, if you take a ratio, it is your dynamic range. So often the maximum stimulus which you can measure, it is limited by the maximum output of the detector which you can handle. And the lower limit is limited by the noise of the system. Now what happens if you're having a very good sensitivity? Let us consider this graph. In the horizontal axis, I am plotting detector input, and the y-axis I have plotted detector output. And this is the very reason I told you why do I prefer to show detector as a separate unit and not with the sensor. Okay, it is easy to understand. So if your curve is like this, the one which is shown in blue color, it is having a certain slope. I have to tell you, if the slope is less, the device is less sensitive, because for a small change in the detector input, it gives you a small change in the output. But if you consider the gray color graph, which is a bit more slopy, right? For a small change in the detected output, you're getting a very huge detected output. So it is having a high sensitivity. Now what happens here? Every curve like this, input output curve of a detector, has a linear region, and it also has a nonlinear region in the higher range and in the lower range. It is true for any detector. And when you are using a very high sensitive instrument, no doubt you are having a very good output from some limited input, but you are reaching your sensitivity limit. This linear limit or nonlinear limits are very fast on either side. So basically, if I draw a line from here, wherever it started getting nonlinear, and the higher side and the lower side, this range is the range where your detector works in a linear fashion. For a very sensitive detector, this linear region is much smaller than or shorter than a detector which is not that sensitive. So if the dynamic range is high, this region is high. A dynamic region is high means the linear region of the detector is high, so that you can measure very feeble and very strong signal. But it comes at the cost of sensitivity. Now, what will you do? Again, confusion. So how many confusions I've created so far? You can make a list. I have created confusion about selection between good sensitivity and dynamic range, resolution, throughput, range, a lot of parameters, and then you come to the conclusion of what specifications you need. And then you go to the step two. Step two is choice or design of the components or the subsystems, validation at the subsystem level. So what is your system? To us, the entire payload is the system, and you're having the parts of the payloads, which are your subsystems. And the system specifications will tell you the designs about the subsystems, which are sensor, detector, mechanical design, electronics design. And here you have to consider different factors like design margin, derating, reliability, redundancy, and safety. I will tell you maybe in a bit more details about reliability later, but for the time being, let me tell you what do I mean by design margin. In the harsh space environment, wherein you are subjected to a lot of disturbances, right, from the process of launch up to in space, certain loads or disturbances your instrument can handle, right? And you can quantify them, how much is the load which is coming to your instrument. And your design can handle much above that load. How much above that load? 1.5 times the load which is expected, 2 times the load which is expected. That ratio gives you the design margin. How much factor the load can be enhanced before your instrument fails. Second point is derating. Derating means other way around. Your component is capable of handling, say, 10 watt of power. But don't design a system in such a way that particular component has to handle 10 watts, because it can handle. You design it in such a way it handles some 6 to 7 watts. Okay, so you're always keeping a margin of its performance. So that is called derating. And reliability, redundancy, safety, we will see. Redundancy I've already discussed. Reliability I will maybe touch upon during the course of my lecture. So after done, you are going to the step 3 right now. So you are going to something called proof of the concept. Proof of the concept means your instrument you have developed in the laboratory, and the instrument is supposed to take a stimulus as an input, and it is supposed to give you an output. So what you do a test, which is a qualitative test. You put some stimulus and see how your instrument is responding. So it is basically a stimulus response check. Step 2, you are now having yourself satisfied, you quantify that how much stimulus you have sent and whether the response is happening, and the response you check with a standard output. There is a fixed reference with respect to the standard output, you check your reference, right? That is the step 2. This is an improvement of your proof of concept model in terms of achieving the specifications. When I am telling I have made a photodetector, it can detect photons, output will be from this volt to that volt. I have to prove that, right? That happens in step 2. Step 3, then you do a more systematic measurement. In steps, you go on giving stimulus in steps and you record the response and you draw a curve. Basically, you are getting a calibration curve and you study what is the stability of the system, whether the repeated observations are giving you the same response, which we call repeatability or precision, accuracy with respect to a fixed measurement, so on and so forth. That makes you makes the proof of the concept. Then coming to the step 4, you have to test your proof of the concept. Many a times it is not possible to test to the complete extent, but sometimes you are able to make a simulation of the space environment with the proper arrangements of the vacuum environment or the proper radiation which the system is supposed to experience when it is sent to space. All this laboratory simulation you can do and test the proof of the concepts. And I tell you, many of the times it is not possible to completely test it in the actual environment which is expected to see in the space. And this step 4 corresponds to our maps to TRL 5. If you go back to that list. Coming to step 5, very important step it is. Proof of the concept now graduates to a prototype or engineering model, EM, by incorporating proper interfaces. I've already told you about a few interfaces, did I not? I spoke about the power interface, right? In the laboratory environment, when you are doing your proof of the concept, you must have used your adapter from your instrument plug point you have used to power your system. In the space environment, you have to replace it with a DC-DC converter. You must have used a computer to take data from the echo data from the instrument. But you cannot send a PC to space, right? You have to have a interface which is called the data interface, spacecraft interface for telemetry, telecommand, and data. You must have used a breadboard kind of arrangement or a Veroboard kind of arrangement. All of us have done during our student lives to demonstrate the proof of concept. But when you're sending to space, You have to have a proper mechanical housing. So all these things are ensuring your step 5, which maps to the TRL 6. So interface definition, I'm continuing. So all these interfaces, whatever I'm telling, have to take the form of an interface control document. And one of the interface is the checkout interface. Checkout interface is for checking, as the name suggests, right? Checkout interface is a ground-based interface which does not fly to space, which allows you to test the performance or the response of your instruments with respect to some stimulus. Okay, that is called a checkout interface, which is important for the ground-based testing. Thermal interface is another interface wherein you do the thermal management of the system. You know how much power is your instrument dissipating. When the instrument is on for some time, you can feel like you feel the fever on the forehead. The instrument is getting hot. That heat, which is dissipated by the instrument, how to deal with it, that is done by the thermal instruments. So all these things culminate to an interface control document. And it is version controlled. If there is some update in the interface or some properties, you have to update this document also. It is imperative. And now in the step 6, prototype or EM testing in the actual environment or the simulated environment, you can test it in the actual environment in the laboratory. You can test it in the vacuum chamber. Okay, these are the simulated environment which I have shown in yellow color. Or you can test it, if you can afford to do it, in a sounding rocket or balloon, or in a PS4 orbital experimental platform, which is specific to Indian context, because ISRO is offering its PS4, the 4th stage of PSLV rocket, for performing experiments on board. So this we call PS4 orbital experimental platform. There's a beautiful name for that, POEM, POEM. So these are some platforms or mechanisms for testing the engineering model in the actual environment or a simulated environment. Coming to steps 7 to test 10, which map collectively to TRL 8. And this is a multi-step process. This is the longest step because in this step, you are basically making the instrument. So far, you have understood the subsystems. So far, you have understood the specifications, defined the interfaces. Now, all these experiences, all these bits and pieces are coming together. So quality and reliability and planning and implementation is coming to picture. Development of qualification model. So basically, you are preparing a model called qualification model. See what happens in childhood when teacher asks us to submit a project. It has to be written in a very good handwriting. Very good pictures have to be there. You have to submit to your teacher, right? Before that, what many students used to do, they used to write in a rough book, right? You don't have the luxury of typing and see how many pages it is taking and what are the pictures it will go. You make a model, which is something similar like the one which is going to submit. In our terminology here, we do similar thing in space technology. We call it a qualification model for design qualification. And based on this experience, we go for making the flight model, which is used in actual flights. And here it is imperative to tell you, I will take 10 to 15 minutes more, not more than that. It is imperative to tell you about the quality as a term, what is meant, and what is meant by reliability. These two are not the same, but they are connected with each other. When I say quality, I mean it is the adherence of a system to the desired specification leading to the user satisfaction. Let us go back to the table, which I have shown you previously. At that time, I have shown you the two columns, parameter list and the desired specifications. Okay, and the desired specifications are all listed here. Now I add the third column here, achieved specifications. You see here, row by row. First row, it complies the requirements. Second row, 10.9 vis-a-vis 10 plus minus 2. It should be between 8 and 12. It is 10.9, almost 11. Fast. Coming to parameter n, it is beyond the specification. So it is not of good quality. Not of good quality. Okay. So that is the concept of quality. What is reliability? Reliability is a probability. Reliability is a probability, and hence it falls between 0 and 1. The probability that your instrument will function or retain to have the desired quality during its desired lifetime. Suppose it is supposed to work for 1 year. Suppose it is desired to work for 5 years. The probability that your system will function with the desired quality at that time is the reliability. So what is reliability? Reliability is a long-term quality. Quality, if you project in long term, it becomes reliability. And this is ensured by a cycle which is called a quality management system, which has a quality assurance plan that I plan to do these steps to ensure that my device or my final product will have a very good quality. That goes as a document, which is called a quality assurance plan or QA plan document. And then you follow the document in every step of your making the instrument. And while you make the instrument, you have a process called quality inspection and control. Somebody is sitting with you who does not care how a good scientist you are. He or she knows that you're at every step, the specification should be this, he or she checks. That is the online control of the quality. And then you make it undergo a process of test and evaluation of your instrument. And the instrument yields you some results. With respect to the test results, you tell whether your instrument is of good quality. And then there is a quality audit, which checks what you planned and what you did, whether you did as per the plan in every step, whether there are certifications from the quality agency, which tells or gives confidence about the quality which is carried forward in every step of the development of the instrument, and what lessons you have learned out of this. And these lessons goes in the next instrument development. So in this process, you develop an instrument, but here there is a play which is coming, a play between the ideal reliability, which is 1. Everybody wants their system to be 100% reliable. Doesn't happen, never happens. Depending on the design, which we call reliability by design, your reliability may be a bit less, say 0.5. But when you are materializing your instrument out of the design, from the design board, when it is on your table, you might find that reliability has become 0.8, actual reliability. Then there is a process of reliability growth. You are not happy with 0.8, so reliability growth mechanism is a review mechanism which detects and analyzes the failures, feedback and redesign the problem areas, and implementation of correcting actions and retests. So it go to the improved probability, which could be better, say 0.95 or 0.94. So this is a continuous process, and this process gives you a product life cycle. Typical life cycle is like this, very simple. You start with the system specifications, you do a system concept review, and then the yellow one is a milestone. You develop your engineering model, and then after the engineering model is prepared, you test the engineering model, and you present the test results of your engineering model to whom? A preliminary design review committee. The preliminary design review committee will review the test results, and they may suggest some improvements. And if the suggestions come, you have to go back here and do the improvements and come back to the PDR. And then with the all satisfaction of the preliminary design review committee, you go to the qualification model development. And the qualification model is tested. Usually it is tested at much more rigor than what is expected in the actual flight. It is basically over tested. Like, before the board examination, when the school takes the test examination, often it is much more difficult than the actual board examination which you are going to face. Concept is like that. And then you have a presentation of the results of your qualification model testing to a critical design review committee, CDR. And then also there may be a process of improvement suggestion. You have to go back if necessary, come back, Once your CDR is completed, then you have to develop the flight model. And the flight model has to be developed in the identical way, let me repeat, identical way as the qualification model. So the process that has undergone to make a qualification model has to be identically followed to make the flight model, because the confidence which you have developed on your materials, into your process, your system, should translate to your flight model. And there is a requirement, there is a importance of process control here. Maybe another 4 or 5 minutes, I will conclude my discussion. I'm almost at the end, and you have to see here in this whole flow chart, I have described step 7, step 8, step 9, and step 10. All are covered in this product life cycle. And reliability growth, as I have explained to you, the very objective of having an engineering model and then to have a qualification model, over testing it, subjecting it to review, go back to your laboratory, making up the flight, make improvements, make the flight model. This is the process of reliability growth. And this is how the model philosophy comes into picture. Model philosophy means the engineering model, qualification model, flight model. This is called a 3 model philosophy. There are other models also, which I am not discussing at the present moment. So ideal reliability you can never achieve, but this process of reliability growth by the proper choice of the model philosophy can help you reach to a good extent to the ideal or desirable reliability. And this is the end of TRL 8 with the readiness of the flight model. So what do you have? You have a compliance matrix. You start with the desired specifications, and with all this reliability increase and improvements, you have come now to the achieved specifications, which are well within the range of the desired specifications. Then you do a calibration from electrical output to the physical value calibration, because at the end of the day, you're interested in what temperature you are going to see, what photons you are going to measure, what pressure you are going to measure, all physical quantities. Output is coming in voltage or current. So there should be a correlation between the electrical output and the physical quantity. So calibration. And sometimes you have to do a calibration on board also. In many cases, in astronomical devices, many celestial objects are used for calibration of your scientific instrument. Ground calibration, in any ways, you have to do. Some instruments have to do, in addition to the ground calibration in space also. Characterization, very important, as I mentioned. Ultimately, what you are measuring has got 3 components in it. The property of the celestial body of the process under measurement, basically that you want to measure. Number 2, in case of remote sensing instruments, the intervening medium's property, which you have to know, right? Third thing is the instrument's property itself. So 3 things combined to tell you what you are going to see ultimately, and you're going to make sense of this whole thing. So instrument property has to be known, and that is done through a set of characterization experiments. And okay, number 4 is complete specification list you have to arrive at. And complete specification list is not only the functional specs, also the specifications of mass of the instrument, power consumed by your instrument, data rate of the instrument, very important. How much data your instrument is consuming, because ultimately you have to transmit from space, right? Mechanical dimensions, because ultimately you have to sit somewhere on the spacecraft. Number 5, quality audit, very important. I have described the process, I will not repeat, but these are the certain things which are necessary checklist for the readiness of your flight model. Number 6, documentation audit. Don't be afraid I'm not going to read everything. You might take a screenshot. This tells you about the product life cycle, which I have shown you a few slides ago. At different parts of the product life cycle, what are the kinds of documents which you have to prepare? Okay, so there is a documentation audit also. And TRL 9 is the final step, flying the instrument to space. And in this process, you develop a flight heritage. So what is the flight heritage? When the scientific instrument functions reliably in space, a flight heritage is created. And when the instrument is in space, what you get from the instrument? You get data from the instrument. What are the kinds of data you get? Housekeeping data through the telemetry channels, which comprises information about different voltages, temperature, which give you confidence about the science data. And along with the science data, you get ancillary data. What are ancillary data? The science data are not enough for scientific analysis. You need to know when this instrument has acquired the science data, where your instrument was looking at. It should not happen. You are doing this, you're desirous of doing the science from moon surface, and your instrument was looking at the deep space. Correct, right? So there are certain supporting information, not the HK data. HK data tells about the health of the instrument. Some supporting instrument which are not science data, but they are all contextual information which are necessary for making sense to your science data. And a new journey starts from here. Now, payload operation and the data archival. So payload is in space, which is a part of a spacecraft or any space mission, and you're getting data, right? And therefrom the mission operation phase starts. The mission operation phase is broadly divided into two parts. One part is the payload commissioning phase. So payload commissioning phase means immediately you don't switch on the instrument with the full extent. Just remember how you're woken up. I don't know really how you're woken up, but children are woken up very gently. They are not woken up with a shake. They're woken up very gently, and that's how a scientific instrument is also woken up, made to wake up in steps by switching on the subsystems, step by step switching on the high voltages, if any. All of a sudden, 2 kilovolt, 3 kilovolt, 6 kilovolt, one should not switch on. Slowly, in steps. Testing of all the operational modes, whether your hand is working properly, neck is working properly, you're warming up, verifying the performance, and then a sort of engineering runs, which will tell you, yes, my instrument is now working as desired in space. My instrument is now verified for performance. And we say that payload commissioning phase is over. Then payload operation phase. So there are nominal mode of operations that their instruments are having different modes of operation. Like you can understand if I set the example of a camera. Camera also has got different modes of operation, like very high exposure image is one example, or very fast imaging is one example, or continuous imaging is one example. Similar modes of operation there for scientific instruments also. Or you may have some requirements of special operations, or in-flight calibration is also an operation. Engineering runs also sometimes you have to do, or as and when necessary you have to do for in the mission operation phase itself. And in this whole process, you go on generating data, and this data are coming in the raw form to the ground station, which we call the raw data. Sometimes we call it level 0, sometimes we call it level 1. These definitions don't take it in a very sacrosanct way. Okay, these definitions are only indicative. So what I want to tell is science data are also having different levels. The raw data is the data as it is acquired from space with science and engineering data embedded. It is called a packet level data. Level 2 is sometimes edited. Edited in the sense the instrument science data at full resolution, the time ordered. Sometimes the data come in bits and pieces. The later data may come first, so you have to do a jigsaw puzzling. So all these things are done, and transmission errors might occur. So those data quality check you can do, and you come up with an edited data set which are a bit usable. Then level 3, you may put some calibration parameters you may have to incorporate, because the data which is coming, they are not calibrated data. They are all elliptical data. You have to put the calibration constants or some corrections you may have to do on the data to make it usable. Then sometime you have to do a process of resampling. That is fresh level of binning. Suppose very high cadence data are coming. You don't need that cadence. You are having data every few microseconds. You need only in 1 minute. So you bin every minutes of data. Okay, these are called resampling. If there is any outlier, remove that. Then you have derived data, means a final form of data. Along with this, you have ancillary data like location of the observation platform. FOV means field of view. and viewing geometry of the instrument, coordinates of the target body, velocities of the observer and the target in the given reference frame, so on and so forth. Because this information also get in the scientific analysis. So to summarize what all we have discussed, let us wrap up and summarize. This lecture has been divided into three parts. In the first part, we have defined what is meant by a scientific payload, and we have introduced the uniqueness of it. We have mentioned about the in situ and remote sensing observations. We have also presented a block diagram, which is a generic construction of the scientific instruments, which is a model which you can fit in with any kind of instruments, roughly. In the part two, we have described step by step the different steps of the scientific instruments. We have introduced the concept of technology readiness levels and mapped the TRL levels, which is step of the development, and also presented to you the concept of quality and reliability and the quality management system in the scientific instruments. We also told you about the importance of the documentation in every phase of the product life cycle. Then we have sent the instrument to space. Then we came to the third part. We have discussed about the mission operations and what all we do. We do payload commissioning in the operation phase. We have housekeeping data, ancillary data, and the science data. Taking all together, one has to do the scientific analysis. We have also discussed about the levels of scientific data archival, and standardization of the data archival is also one thing which I have to make a mention of. There are certain standards. One standard is PDS standard. Okay, so planetary data standards is PDS, wherein people know what are the folders available, what format data are saved, what to look for if I have to look for any caveat of your instrument. So I don't have to explain to anybody. After 50 years, 100 years from now, those data archival will remain, and then standardization will ensure that the way I have archived the data has relevance after 100 years from now. Okay, so these things we have discussed, and we will end this journey with a statement like this. A great discovery is made. A great discovery is made after a planet is probed by an instrument which is calibrated to the best possible accuracy with its quality and design margin, speaking of its reliability, which is designed to meet the stringent specifications translated from a scientific concept silently born in the mind of a scientist. So if we have remembered my first lecture, wherein I started from the philosophy, then came to the space exploration gamut, and then today I have shown you how science, technology, and management, they go hand in hand to materialize a certain thing in a standardized way. And thank you very much for your kind attention, and I'm ready to take the question.